My name is Jacob Garza.
My name is Christine Padilla.
My name is Jada Joseph, and this is our project on thermodynamics. Thermodynamics is a branch of physical science that deals with relations between heat and other forms of energy. There are 5 main subunits when it comes to thermodynamics. Let's start with thermodynamics itself.
Thermodynamics has a few laws. The first law of thermodynamics states that the change U in internal energy of a system equals the net heat transfer into the system minus the net work by the system. It also states that the energy cannot be created or destroyed, only conserved. The second law of thermodynamics process states that the state of entropy, which is the measure of a system's thermal energy per unit temperature, that is unavailable for doing useful work. Of the entire universe as an isolated system will always increase over time. The second law always states that the heat transfers from hot to cold, but how does heat actually move? First, there is conduction, which is simply the transfer of heat by two things touching. Second, there is convection, which is the transfer of heat from one place to another by the movement of fluids. Finally, there is radiation, which is a form of energy transport consisting of electromagnetic waves traveling at a speed of light.
Next, we have temperature, which is the degree or intensity of heat present in a substance or object, especially as expressed according to a comparative scale and shown by a thermometer or perceived by touch. This heat is thermal energy being transferred through conduction, convection, and radiation because of the difference in temperature. While internal energy is the sum of kinetic energy and potential energy stored in a system, with all this heat and temperature, how do you calculate it? A simple change in temperature is calculated by subtracting the final temperature from the initial temperature. To convert from Fahrenheit to Celsius, deduct 32, then multiply by 5, then divide by 9. Celsius to Fahrenheit, multiply by 9, then divide by 5, then add 32. A basis for these calculations is absolute zero, where all atoms have been completely stopped relative to each other and corresponds to the number 0 on the Kelvin temperature scale. An object cannot be cooled below this point because there is no atomic thermal motion left to stop.
This temperature change, how does it actually affect objects? That's when state changes, and I don't mean people wanting to move to California. There are 6 different state changes. First, we have melting, which changes solids to liquids. Then there's freezing, which changes a liquid to a solid state. There's condensation, which changes gases to liquids. Vaporization, which is the liquid to gas. The heat of vaporization is the energy required to change a liquid into a gas at its boiling point. The heat of a fusion is the amount of energy required to change a solid into a liquid at its melting point. Then there is sublimation, which is the direct change from solid to gas. And finally, deposition, which is the direct state change from gas to solid. Each of these substances have triple points that are different for each substance because it takes a distinct temperature to form these substances. Such as the anomalous properties of water are those where the behavior of liquid water is entirely different from what is found with other liquids.
Sticking with the movement themes, let's move on to heat expansion. When a material is heated, the kinetic energy of that material increases and its atoms and molecules move about more. This means that each atom will take up more space due to its movement, so the material will expand. The dependence of thermal expansion on temperature, substance, and length is summarized in the equation delta L equals AL delta T, where delta L is the change in length, delta T is the change in temperature, and A is the coefficient of linear expansion, which varies slightly with temperature. The specific heat capacity are joules over kilograms times Celsius, or equivalent to joules over kilograms times Kelvin. The heat capacity and specific heat are related by the equation C equals Cm, or C equals C over M. The mass, M, specific heat, C, change in temperature, delta T, and the heat added or subtracted are related to the equation Q equals mc delta T, where water has the highest specific heat capacity of any liquid. Specific heat is defined as the amount of heat 1 gram of substance must absorb or lose to change its temperature by 1 degree Celsius.
Finally, we have our last subunit, transmission of heat. Heat is transferred via solid material, conduction, liquids and gases, convection, and electromagnetic waves, radiation. Heat is usually transferred in a combination of these three types of seldom occurs on its own. Heat is absorbed or radiated through a process called endothermic. This process relates to a sponge soaking up water in which heat enters an object, warming it. The longer the object is exposed to the heat source, the more heat it absorbs. Greenhouse gases warm the atmosphere by trapping heat. Some of the heat radiation from the ground is trapped by greenhouse gases in the troposphere. Like a blanket on a sleeping person, greenhouse gases act as an insulation for the planet. Newton's law of cooling states that the rate of heat exchange between an object and its surroundings is proportional to the difference in temperature between the object and the surroundings.
And that's on thermodynamics.
Thank you for listening to our TED Talk.
Period.